So, welcome back to our video lectures on projective geometry. Last time we learned about Cayley Klein geometries, about measurements in those geometries, and this time we will care about transformations in Cayley Klein geometries. So we will approach the question, what are reasonable movements in such geometry that leave both lengths and distances invariant? So to do so, I first want to do a kind of recap on what we learned about projective transformation in the just general projective plane RP2. So we learned that whenever we have a projective transformation tau, it is associated with a 3x3 matrix that is applied in different ways to different objects. So for the points, we say the transformation that comes from our matrix M is simply take your homogeneous coordinates of the points and multiply them by the non-degenerate 3x3 matrix M. In order to preserve incidences before and after the transformation, the corresponding action that we have to do on the level of lines is to take their homogeneous coordinates and multiply them by the inverse transposed of that matrix. You can easily check if you do that, then if a point and the line is incident before the transformation, it will also be incident after the transformation. In a similar way, we have to deal with conic. So conic is represented by a symmetric matrix A, primal conic. And if we want to preserve incidences of a point and a primal conic under a projective transformation, we have to transform the conic matrix in that way here, that from one side we multiply with the inverse transposed and from the other side we multiply with the inverse. You remember we introduced conics in a kind of dual way, such that we said we need two matrices to describe them, in particular for the degenerate cases, the primal conic and the dual conic. The dual conic describes how we can express tangencies of lines to this conic, and the dual conic is transferred in the following way by multiplying the transpose of the transformation matrix by the dual conic matrix by the original transformation matrix, and you can easily check this preserves tangencies. So let me just give a little example of how projective transformations interact with the objects. So assume we have this configuration that you see here. You have 2 points and a line through them, a conic and the 2 intersections here. And now you map this picture to a situation where, for instance, the 2 points get mapped to 2 new points. Then you immediately know where your line is mapped, because the mapping is defined in a way such that incidences should be preserved. The conic may go to any other situation here, depending on your transformation, but if you look at those point x and y, you see they will, if they are the intersection of the line and the conic before the transformation, they also have to be the intersections of the line and the conic after the transformation. It's a little bit tricky to figure out in which order they appear. That depends on the sign of certain cross ratios. I don't want to go into that point here. One more important point here, I simply want to stress once more that the actions on the objects are defined in a way such that you always preserve incidences and tangencies, which were our fundamental projective properties. Another important point, also transformations are transformed. So if you have a transformation that acts on some points and lines in the world before you did the transformation M, so let's call this transformation N, then after you applied M, this transformation here becomes a different transformation matrix. So consider transformation as a unique projective entity that also has to be transformed in a way. And here, notice an important difference. Transformation is transformed in a way such that from one side you have to multiply with m, and from the other side you have to multiply by m inverse in order to preserve all properties. You can easily check that. Okay, second recap. How did we calculate distances and angles? So this will be a really quick one. So if you have Cayley Klein geometry with its fundamental object, and you have 2 points, and you want to calculate the distance between these 2 points, you draw the join of those 2 points, you intersect it with the fundamental object, you get your 2 points x and y, and you take the cross ratio of those 4 points, take the logarithm of that, multiply it by your cosmetic constant, and get the distance of the 2 points. I want to mention a fine point here that I haven't discussed earlier, talking about the sign of this expression here, because you see, if I interchange x and y, then the cross ratio here becomes its own reciprocal, and the logarithm causes a sign change here. So whenever we have information on the order of x and y by some external source, it makes sense to speak about signed distances here. So for instance, if we consider this line here as an oriented line, but whenever we don't have this information, it only makes sense to speak of absolute values of such distances, and only considering this expression here up to sign, where we simply don't know whether the x is here and the y is here, or vice versa. In completely dual way, we defined angle measurement. If you have 2 lines and you want to measure their angle, you take their meet, take as a dual operation to taking the intersection here, take the 2 tangents through that meet to your fundamental object, take those 4 lines and calculate the cross ratio, take the logarithm, multiply by the constant, and call that angle. Again, also here it makes sense to consider angles only up to a sign change, since we don't know how the implicit order of x and y will be. It only makes sense if we have an orientation around that point given by some external reasons. Okay. So here I wrote it once again. It's reasonable to consider measurements only up to sign, and in what will follow, I will only consider the absolute values here. Okay, now we will take together these 2 threads, so the projective transformation thread and the thread of distances and angle measurements. And we are asking for what are reasonable transformations within a Cayley Klein geometry. How should such transformations be defined? And one natural way is to say it's those transformations in the projective plane RP2 that keep distances and angles invariant. So before and after the transformations, distances and angles should simply be the same. So assume you have a fundamental object, and now let's see what happens to distances of points under a transformation. So assume you have 2 points. I told you how to measure the distance between these 2 points. It's just this formula here. Now assume you have a projective transformation, and now let's ask the question, what is the distance of the 2 transformed points? Well, you can easily answer this question, since it's simply applying the same formula here, now with the role of P and Q replaced by P prime and Q prime. So you calculate P prime and Q prime as the projective transformations of P and Q. With that, you now have 2 possible ways to determine your line L prime, that is the join of those two points. One of them is to say, well, it's just the image of the join that you had before the transformation, or you can simply join the two transformed points. Then you have to get points x prime and y prime for your measurement, and they are, I use a little abuse of notation, the intersection of your line L and the fundamental object F, and I intentionally wrote them here as two-element set because we don't have an a priori information which is the order of these 2 points. So with those 2 points, you can now again, even if you just consider them as pair, determine the distance up to a sign by simply applying the formula for the distance measurement. So after the transformation, the 2 transformed points will have this distance, and if you consider it only up to sign, the order of x and y does not play any role. Okay, now we ask the following question. When do we have the case that before and after the transformation we have the same distance measurement? I ask that not for a specific pair of points, I ask that for all pairs of points. So what is a property of a transformation that it must have to preserve distances? And here comes the important concept that governs the idea of Cayley Klein transformation. It's the following. If you have a fundamental object and it's defined by a primal dual pair of matrices describing the fundamental conic, then I explained to you how to transfer those fundamental object matrices here with respect to our projective transformation. So there is a nice way of defining what is f under the projective transformation. You take the transforms of the A and the B, considered as a primal and a dual conic. And if this transformation is again your fundamental conic f, then you call this an F transformation, which should be a transformation of the Cayley Klein geometry associated with this specific fundamental object. So you ask for transformations that leave the fundamental object invariant as a whole. So you apply the transformation, the object gets mapped to itself, and this is called an F transformation. And now the following happens, that up to a possible sign change, the length measurement before and after the projective transformation, if it is an F transformation, is exactly the same. So for F transformations we get that, well, these pairs of points that you have here, this x prime and y prime, they are the intersections of L prime. And you remember, L prime was the image of L, and F prime, but F was also the image of itself. So these intersections here have to be mapped to the 2 transformed images of x and y. Again, we cannot say something about the order in that situation, but the pair here remains the same, and so what you get is you get a length invariant up to a sign. And you can do the same reasoning also for the angles, and by that you see that these transformations that leave the fundamental conic invariant are length preserving and angle preserving. You may recognize how cool and important that is, because by this definition of an F transformation, we don't have to speak about points and lines and angles in our geometry and about measuring distances. We can solely speak about the fundamental object and how it is transformed. So the question of studying transformations that leave distances and angles invariant is reduced to those transformations who leave F invariant. In the Perspectives of Geometry book, you will also find a proof that this characterization is one by one characterization, so you can also prove that all the transformations that are distance and angle preserving are actually such F transformations. So next question that arises here is, which transformations do leave F invariant? And again, we have to study our 7 different cases of how conics are classified up to projective transformations. So if we understand those 7 cases, we understand everything for all conics, because these are the 7 cases that cannot be projectively transformed in each other. And so if we have an arbitrary conic and we want to study the transformations of this associated Cayley Klein geometry, we first look to which of those cases does it belong. Then we transform it to that case, take our classification here, and transform the set of transformations back to this arbitrary conic. So you see, it's sufficient to study these cases up to projective transformation, and again we have to distinguish our 7 cases, and at least I will show you how these transformations look like for some of those situations that you get here. So let us start with the first case, which is the non-degenerate real conic, and our prototype for a non-degenerate real conic was the unit circle, and these here are the equations, the primal and the dual one for the unit circle. So our fundamental object consists of 2 matrices which are the same in this situation, representing the points and the tangents of the unit circle. And what we now ask, which transformations leave this conic defined by this primal and dual matrix invariant as a whole? And this should trigger a kind of déjà vu effect, because we dealt with that. In one of our earlier lectures, we studied which transformations leave a real non-degenerate conic invariant, and we learned the set of all projective transformations that leaves a real non-degenerate conic invariant is isomorphic to the transformations of RP1. So you hopefully remember that we associated the line defining this conic with an RP1 line by viewing the points on that conic from the perspective on a point, and it turned out that all projective transformations of that conic were given by the image pre-image pairs of 3 points. So in particular, we see that we have 3 degrees of freedoms in this situation. So in principle, we completely understand how the Cayley Klein transformations for that conic here work. It's just the same up to isomorphism as the transformation of the real projective line. Here comes another déjà vu. You may remember from another slide that we learned that these transformations here are essentially the same as the transformations that leave a fixed circle in the complex projective line invariant in CP1. And we had this extensive part of the lecture where we explained the differences between the CP1 world and the RP2 world, but that agree along this conic. And we will later on learn that this equivalence that we have here links 2 different models of the hyperbolic Cayley Klein geometry. The one model is called the Beltrami-Klein model. We will learn about that in a later lecture. And the other one is Poincaré model. And both agree on the boundary of the conic, and both differ in how the world around the boundary looks like. We will come to that in one of the later lectures. So take-home message here, we really understand how these transformations work. They are isomorphic to the transformations on a real projective line, they have 3 degrees of freedom. Second example, elliptic transformations. This time we are in the situation where our conic has only complex solutions. So the primal and the dual conic is of this form here, x squared plus y squared plus z squared equals 0. And we know this has only complex solutions, and both the distance and the angle measurement will be elliptic. And this time we ask for those transformations that leave a complex, non-degenerate conic invariant. And this sounds pretty complicated, I must admit. So we have a complex conic and we're looking for projective transformations acting on that conic. And as a matter of fact, it is not complicated. It is the easiest case of all of them due to the simple form of those quadratic forms here. So if you look at the primal and the dual matrix defining this conic, it's just the unit matrix. And if it's just the unit matrix, then we are looking, remember how dual conics transforms for a matrix, for a transformation matrix M that leaves the unit matrix invariant. And you see you have a unit matrix in here. You can equally well omit it. So what we are looking for is transformations of the type, they are non-degenerate 3 by 3 matrix with the property that M transpose times M is the unit matrix. And if you attended your linear algebra classes, you know these matrices. These are just the matrices in the orthogonal transformation group. So in other words, these are 3-dimensional rotations or reflections. So these are matrices that take an orthogonal system of basis vectors again into an orthogonal system of basis vectors. And so the question is, what are the vectors here? These are just the vectors of the homogeneous coordinates of our points and lines in our space. So essentially these rotations and reflections that we get here are applied to the homogeneous coordinates, and it's the best way to consider this transformation not taking place in the standard embedding of our projective plane, but taking place on a sphere to which we map the standard embedding. So here I've taken a picture from one of my favorite books of Cayley Klein, his lectures on non-Euclidean geometry, where he explains how this transformation looks like, or how you relate the sphere to the standard embedding. So imagine you have our standard embedding and say here is the origin of our coordinate system. So whenever you have a point in this standard embedding, say the red point here, then we identified points up to scalar multiple. So up to scalar multiple, you can identify this point with 2 points on the unit sphere that are in antipodal relation. So every point on the projective plane gets an antipodal pair of points here on the sphere. And what we're asking for, if we're talking about elliptic transformation, is rotations or reflections of that sphere. I want to show you some picture here. So actually in that picture, lines in the standard embedding, lines in the projective plane, are transferred to great circles on the sphere, so equatorial circles, so circles of full diameter on this sphere. And our walking in unit steps that we did in our previous lectures, in that space is simply, walking in unit steps in the sphere, which means you walk along that great circle by going in same distances along that circle. And if you do so, eventually you will meet your antipodal at which you started your walk. So you see, this world of elliptic geometry is really best understood on the sphere, and the transformations are really nothing else as the rotations and reflections of this sphere. Little remark here, as in the hyperbolic case, we essentially have 3 degrees of freedom. If you rotate a sphere, there are 3 parameters that manage the rotation, and this group here is somehow subdivided in 2 parts, in the purely rotational part and in the reflectional part. So, third geometry, the Euclidean case. So, in that case, we have the situation that we have a degenerate primal conic, which is a double line, and we have 2 complex points on that primal conic. So the primal conic is defined by this rank 1 matrix, and the dual conic is defined by this rank 2 matrix in our standard representation. And you should recognize this is essentially our line at infinity that we have here with the 2 points I and j on it. And all tangents to the fundamental objects will be lines through I and j. So now again we are looking for transformations that leave these objects invariant, and again in that case it's better to look at matrix B than at matrix A for 2 reasons. First of all, our transformation isn't inverted in the application to B, and second, B is less degenerate than A, and so we're looking for transformations such that M transpose times our matrix B times M is again our matrix B. And it turns out that those transformations have this form here. If you look in the perspective book, you can read the proof for that. Let me have a little closer look at this matrix. If you apply that to a standard embedding of the projective plane, what you get is here a little Euclidean rotation matrix. So you get rotations of your objects, and you also get a translation part that moves your objects around, and you get a scaling part. So this time you have 4 degrees of freedom due to the fact that your fundamental conic is a little bit more degenerate than in the case of hyperbolic or elliptic geometry. Actually, I've written only the rotational part here. There's also a reflectional version of that, which has a plus here and a minus here. So the transformations are composed of these 2 types of matrices. So I want to end this lecture with an interesting visualization that exemplifies the difference between the Euclidean and the elliptic case. So you see 2 images here, and both images look the same for the moment, and this will change very soon. But I first have to explain what you see here. So let's again take this picture of the Cayley Klein book. So here you have the standard embedding, and the standard embedding is shown here on the right side, and as an image I take an infinite pavement of the plane with these clock images. Then you have the projection of this plane to the sphere by projecting through the center to the sphere, and you get this image here, which is the top view of the sphere. So we look with a viewpoint coming from here to that sphere. And you see you have the same situation here, and this is considered to be the starting situation for a movement that we will apply. And in both pictures we now apply 2 different kinds of movements. So here it is a Euclidean motion where we just have 1 parameter t, which corresponds to translation, which will shift our clocks here in that direction. So imagine this infinitely many clocks moving in the standard embedding plane, and all the time we will project to this sphere here. And in the second picture, you have an elliptic motion, and here you see a rotational matrix depending on an angle alpha, and I will increase this angle alpha, which causes a rotation of the sphere. And now let's look how these two motions apply in the two cases. So you see they look very, very different. So up here you have the Euclidean motion that moves these infinitely many clocks in one direction, and it looks slightly unnatural in the spherical picture because you take these infinitely many clocks that you hardly see here at the boundary and shift them to the center of the sphere. That's like moving this plane with the infinitely many clocks on top of the sphere and always projecting. In the elliptic case, we see that we get a rotation of the ball. I hope you recognize that this really is just a rotation that induces a kind of very, very distorted perspective transformation here in that world. So it looks like you have two copies of your world in two planes, in one without mirror images and a second plane with mirror images, like two planes on top and bottom of the sphere, and you rotate them around, and this is what you see here. And every time the line at infinity passes through that picture, the corresponding squeezed objects start to go through the circle on the other side. This ends our little excursion on projective transformations that are Cayley Klein transformations. In our next lecture, we will take all our knowledge about Cayley Klein geometries together and do some Cayley Klein elementary geometry. See you there!